Alright, welcome. In this video, I'm going to be working Algebra 2 Homework 9.2, which is all about logarithms. And I guess what we're going to do, we're going to get out our own separate sheet of paper, and we're just going to get to work. So we're going to start by finding the value of the common logs. Okay, by common logs, we mean logs with base 10. So remember what I said in class, if we see that log and it doesn't have a base on it, we assume it means 10. Okay. It's not a terribly popular logarithm in mathematics. It is kind of popular in science, so we need to be able to work with this one. So the first one, log with base 10 and argument 1. Okay, what we're doing is we're going to say, well, I guess this is going to be eventually equal to something. The question we're asking to ourselves off to the side is, what exponent do I put on 10 to get 1? We're going to put the 0 exponent on 10 to get 1. So the log with base 10 in argument 1 is 0. I think I told you in class the log with base 10, with any base in argument 1, like the log of 1 is always equal to 0, regardless of what the base is. Okay, so log base 10 of 0.1. Okay, so what we're going to do over here, we're going to say 10 to what power equals 0.1. Well, 0.1 is 1/10. I think that's going to be a better way for us to look at it. And say, what exponent do I put on 10 to get 1/10? That's going to be the -1 exponent. Okay, for C, the log with base 10 of 0. Okay, I'm going to put equals because this one's not going to exist. Okay, so I'm thinking, what exponent do I put on 10 to get 0? Okay, and there's no exponent you can put on 10 to get 0. Okay, you put a positive exponent on 10, it's going to be a positive number, right? If it's bigger than 1, it's going to be bigger than 10. And if you put a negative exponent on 10, it's just going to be 1 over some power of 10. So, there's no way that we can have a power of 10 come back 0 or negative. So it's not equal, it's just not existing. So I'm going to say D and E does not exist. Right, for D, the log with base 10 of 1,000. Okay, that's going to be the exponent I put on 10 to get 1,000. That'll be 4. I'm going to go a little faster through the last couple of these. Okay, the log with base 10 of the cube root of 100. Well, that might need a little bit more work. So I'm going to go over here and I'm going to say, all right, 10 to what power equals the cube root of 100? Well, 100 is a power of 10. I'll figure out some way to deal with the cube root after. So I'm going to say that this is the cube root of 10 to the 2. And then you might think back to, okay, the last unit, hey, we wrote this as 10 to the 2/3 power. Okay, so 10 to the what equals 10 to the, okay, I'm going to put the 2/3 exponent on. Okay, so that's going to equal 2/3. Oh. Yeah, like that. Then F's going to ask for the log with base 10 of 1 over the square root of 10. Okay, and okay, for that, saying what power of 10 is 1 over the square root of 2, what we call the square root, the 1/2 power, and 1 over something makes that a negative power, so that's going to be -1/2. 2 is find the value of the natural logs. Remember, a natural log is a log with base e, where e is that weird number between 2 and 3 that mathematicians are interested in. So, natural log of e, okay, that's the log with base e of e. Okay, so what we're thinking is, what exponent do I put on e to get e? Well, e is just e to the first power, so I'm going to put the 1 exponent on there. Natural log of e to the 6 is equal to log with base e and argument e to the 6. So I'm saying, what exponent do I put on e to get e to the 6? This is really getting at that fundamental identity we talked about. You know, the log with base b of b to anything is just going to be that thing. So this is going to equal 6. All right, and see, log of the square root, pardon me, natural log I have a bad habit. Anytime I say log outside of like Algebra 2 class, I mean natural log because it's really the only log I care about. But log of the square root of e, natural log of the square root of e is log with base e of, maybe I'll write the square root of e as e to the 1/2. So I'm saying, what exponent do I put on e to get e to the 1/2? That's going to be 1/2. Or you could look at it as the log base e and e to the 1/2. They kind of cancel each other off with that fundamental identity. However you're thinking, it's going to give you 1/2. Is natural log of 1 over e to the 2. Okay, so that's log with base e. And argument, all right, I can write that as a negative power of e. If I've got 1 over e squared, that's the same as e to the negative 2 power. Okay, that'll be negative 2. Because I'm thinking, what exponent do I put on e to get e to the negative 2? I'll put the negative 2 exponent on e. E natural log of negative 1. This is going to be a lot like it was, I think we tried to take the common log of negative 1 earlier, right? No, we took the common log of 0 and found that didn't exist. All right, so we're thinking e to what power equals negative 1? Okay, let you think about that. E is a positive number between 2 and 3. And kind of like 0, this one's not going to exist because e is a positive number, and any power of a positive number is going to be positive. Any real power at least. And so over here I'm not going to say equal, I'm just going to say it does not exist, right? E to any power is always positive. It's negative, it's never negative and never 0. Okay, so I'm going to say the natural log of negative 1 doesn't exist. Last one here is going to be natural log of e to the x plus 1. That's log base e of e to the x plus 1. And again, kind of like the other ones, you could look at this in terms of the identity that we learned about, that, you know, the natural log of e to the u is just always equal to u for any u. So you could just say this is going to be x plus 1, or you could look at it as what exponent do I put on e to get e to the x plus 1. Okay. Either way, it's going to lead you to believe that this log comes back x plus 1. Just remember, the log is the exponent. I didn't say it during number 1, but I'm kind of surprised. The log is the exponent we're putting on whatever to get the desired result that's in parentheses. All right, number 3 is going to be very similar. Take some logs, but this time the base is 2. Right, so log base 2 of 32. I'm thinking to myself, 2 to which power equals 32? Okay, 2 to the 5th power is 32, so this log is equal to 5 because the log is the exponent that I use to get what I want. All right. Log base 2 of 0.25. And I'm going to rewrite that. 0.25, that's 1/4. Okay, if I want to make this most obvious to myself, it might be nice to just write 1/4 as a power of 2. Okay, so 4 is 2 squared. So this is like 2 to the negative 2. And that'll be negative 2. The next one is log base 2 of root 2 over 2. And I don't know. There's a number of ways to think about this. Maybe it's a number you recognize that's the same as 1 over root 2. You know, however you think about it. I'm just gonna look at that, you know, through the lens of the exponent rules. So square root of 2 is 2 to the half. This is 2 to the 1. Okay. And when we're dividing two things with the same base and different exponents, it's when we subtract the exponents. So 1/2 minus 1 is negative half, and then with that fundamental identity, this is going to be negative 1/2. Okay. It is log base 2 of square root 8. And I'm thinking, I'm just going to write that fundamental identity right there, because I'm just going to be using this repeatedly. I'm going to rewrite all of these as powers of 2. And log base 2 of, okay, square root of 8 would be the square root of 2 to the third. So that's 2 to the third to the 1/2 power. Would be 2 to the 3/2. And so that's going to be 3/2. E is log base 2 of 8 cube root of 2. And that will be log with base 2. 8 is 2 to the third times cube root is 2 to the 1/3. Okay? We're multiplying two things with the same base and different exponents. That's when we'll add the exponents. And say this is log base 2 of 2 to the 3 and a third. So 3 plus a third, 3 is 9/3, an extra third would make 10/3. And that will be 10 divided by 3, 10/3. And the last one here is log base 2 of 1, that's going to be 0, but I'm still going to write it out and use that fundamental identity. Okay, so 1, I could write that, if I wanted to, as 2 to the 0, and then I could use that identity and say, okay, that's 0. Or you just remember that the log of 1 with any base is going to be 0. Okay, next we're going to rewrite the exponential relationship as a log equation. And for us, that's just going to look like using the definition of a logarithm. So remember that log base b and argument a equaling x is equivalent to base to the x power. Remember, the log is the exponent. That's equal to a. Okay, so that's what we're going to be using here. So a 2 to the 4 equals 16. So I'm going to write it as a log equation. I'm just going to kind of stick to what I've got. The log, and the base of the log is the base of the exponential, so that's 2. The argument is, what this thing is equal to. And the log is the exponent. For b, if 3 to the negative 4 equals 1 over 81, that means log base 3 of 1 over 81 is equal to negative 4, because I put the negative 4 exponent on 3 to get 1 over 81. Okay. And then c, 10 to the 3/2 equals 10 root 10. Let's put this down here. This won't take that much room. That'll be the log with base 10. You can write base 10, or you could just write no base, right? Because that means 10. Of 10 root 10 is equal to 3/2, because the log is the exponent. Because 10 to the 3/2 equals 10 root 10, whatever log we're taking is going to equal 3/2. In number 5, we'll be doing the opposite thing. We'll be rewriting the logarithmic relationship as an exponential equation. Okay, so the first one, I could have used, the spacing on this one's pretty poor. So wait a second. The middle one's not even a logarithmic relationship. That's too bad. Oh well. Can't go back now. For a, log of 100 equals 2. Well, we know that that means log base 10. Okay, so the base of the log is the base of the exponential. Whatever the log is equal to, that's going to be the exponent. And that's equal to 100. And that makes sense. That's true. Okay, so let's see. Okay, pretend you didn't see that, or can't see it on your paper. So that's natural log of 1 over e equals negative 1. Okay, just going to approach this like didn't just see the answer. So log of 1 over e is, and natural log of 1 over e equals negative 1. That's like saying log base e of 1 over e equals negative 1. So this is saying it's okay, the base of the log is the base of the exponential, e to the negative 1, because the log is the exponent that we put on to get the result. Okay, e to the negative 1 is 1 over e. And then for c, log base 2 of 8 equals 3. Okay, so the base of the log is the base of the exponential. Okay, the log is the exponent, and the argument is the result. Okay, 2 to the third equals 8. That's true. That makes sense. All right, next we're going to give a sketch of the graph of y equals f of x. Okay, so first is f of x equals natural log x. Now, in class, in video, I'll show it a little better. But in class, I kind of just showed you the shape of the graph, showed you the x-intercept, and was like, okay, there you go. I didn't have much time. But for this one, I'll give you a slightly better sketch, but there's really not that much to draw here. So we really are only going to be interested in the right half of the plane. Because as I told you, the domain of log of x is going to be x is greater than 0. Okay, so I don't need to be looking at any place where x is less than 0. All right, and what happens here is it has a vertical asymptote at x equals 0, and then it looks kind of like an exponential curve, except it's sideways. This x-intercept here is at x equals 1, and then it's natural log x, which is log base e of x. So one thing that you could do is you could label kind of the spot where it hits 1. Say that's 1. Blow out of proportion. That would come at x equals e, right? Because the log with base e, and argument e is going to be 1, we put the 1 exponent on e to get e. And yeah, that's going to be as good of a graph as we can draw. For b, I'm going to say, all right, I'll just draw another one. It's going to look almost exactly the same. The difference is going to be that point right here is not going to be at x equals e. It's going to be at x equals 10, because log of x without any base indicated means log with base 10. I'll tell you, actually, in the really old textbooks, when they said log x, they meant natural log x, but I just leave that there. This is still going to have an x-intercept at x equals 1, but it's going to, the difference here is that it just really, turns over a lot quicker. And so, maybe that's going to be 1. This graph, that would be over here at x equals 10. Because the common log, the log with base 10 of 10 would equal 1. Because 10 to the 1 equals 10. All right, and the third one, f of x equals log with base 2 and argument x. The same thing, it's going to be all the same, except the location of that second point. So I'm going to just put in 1 here, and it'll have to be about like that, and maybe 1 is up here, and that's 2. I don't know. That wasn't my best sketch ever. But I made that one a little too tall. But it's okay. If we label it, it can be whatever we want. But I think before I move on, I do want to point out, because all 3 of these were just logs of regular x. The argument was just x. The inside of the logarithm was just x. The domain of all 3 of these functions was just x is greater than 0. I might as well also point out that the range of a logarithm function is going to be all real numbers, because you can put any exponent you want on a positive number. Suppose the log with base b and argument m is equal to 12. Find the values in terms of m. Okay, yes, I like this problem. I remember where this comes from. I think what we're going to need to do is we're going to need to kind of use the definition of a logarithm and, get some sort of true equation in terms of b, m, and 12. All right, so I brought back the definition of a log. And we're going to use that to write down the key fact here. And that's going to be, okay, if log with base b of a is x, then log means b to the x equals a, then log base b of m equals 12 means that b to the 12 equals m. So when we're asked about b to the 12, that just equals m. For b to the 6, well, okay, to 12, 6 is half. So this is b to the 12 to the 1/2. And that would be m to the 1/2, which is going to be the square root of m. Okay, now, you might just stop at m to the 1/2, and that's fine, right? But I need you to be able to recognize, say, on the multiple choice section of a test, that m to the 1/2 is the same as the square root of m. All right, so for C, I've got b to the negative 12. Okay, so that's going to be b to the negative 12 is equal to b to the 12 to the negative first power. Okay, that's going to be m to the negative first, and that's 1 over m. Again, you're free to stop there and just leave it as m to the negative 1, but you need to be able to recognize that m to the negative 1 and 1 over m are the same thing. So D is b to the 24th power. Okay, b to the 24th power is going to be to b to the 12th. That'll be squared. And that's going to be m squared. Not really anything we can do with m squared. Just m squared. Okay, 1 over b. Yeah, like that. Okay, 1 over b is equal to b to the negative first power. And, all right, I have to do something to b to the 12 to get it to negative 1. I'm going to take negative 1 over 12, right? Just need to figure out some exponent to multiply it by. Okay, because b to the 12 is equal to m, this will be m to the negative 1 over 12. This will be 1 over the 12th root of m. That was a good one, I like that. And then the last one, square root of b. Oh, yeah. It's going to be b to the 1/2. So I think, whoops, not 12. What power do I need to take b to the 12 to get b to the 1/2? And I think that would be 1 over 24. Because 12 divided by 24 is the same as a half. Okay, yep, so that's going to be m to the 1 over 24, and that'll be the 24th root of m. Now the last two problems are going to be kind of some of these problems that start off with a function and ask us some different questions about them and then culminate in, hey, sketch the graph. So we're going to start by finding the domain and range of f, where f is the common log of x plus 5, the log with base 10 of x plus 5. In fact, maybe I'll even write it like that. Okay, now I'm going to, find the domain and range. All right, for domain, I'm going to grab the argument of the log, x plus 5, and I'm going to set it greater than 0. 10 to any power has to be positive. And so that's really what I got to think of each time I plug something into f of x is, like, what exponent am I putting on 10 to get this number? And so it doesn't make sense. Your answer, or your question has no answer when you're trying to ask that about a negative number. So that's why we need x plus 5 to be a positive number. Also didn't work when that number's 0. Okay, so the range, oh no, we need to solve this. So we're going to subtract 5 from both sides, and that's x is greater than negative 5. The range of this function is all real numbers, because the domain of an exponential function is all real numbers. I'm kind of just going to say that this unit, and you can just remember the range of a log function is all real numbers, because we haven't talked about inverse functions yet. I'm just kind of planting those seeds in your mind for when we talk about them a couple of units from now. So in B, we're going to find the y-intercept on the graph of f. Okay, so y-intercept, that's where x equals 0. Okay. So, I don't know. Either way, f of 0 is going to be the log with base 10 of 0 plus 5. And that's the log with base 10 of 5. And maybe I did this on purpose. Just to point out that this is not 2 or a half or really any sort of good number, right? Because I have to think to myself, what exponent am I putting on 10 to get 5? Well, 10 to the 1/2 power isn't half of 10, it's the square root of 10, which is going to be just a tiny bit bigger than 3. And that's not 5, okay? And so it's going to be somewhere between 3 and 4. Right? No. No. Definitely not. It's going to be less than 1. I don't know what I was thinking there. I was thinking about 2. Pardon me, just ignore that. Yeah, this is not... oh, yeah, no, square root of 10. No, there's no power I can put on 10 to get 5. It's a bad number. If you go and bring in your calculator, I'll show you there's actually a button. So you can go into, I think it's math, and yeah, you go kind of up from the top because it's pretty down low. You can do log base, and you can do log with base 10 and argument 5. That is really not the point of our algebra course. We can see that this is just 0.699 or 0.698. It's a number between 0 and 1, which is kind of what we would already knew anyway. I'll show you a different way that you could calculate logs on a calculator if you didn't have a nice graphing calculator that had that log base function. But overall, this class, we're really interested in computing logs without the use of a calculator. So that's going to be all for this video using a calculator. C is asking for the x-intercept. Whoops, I'm still writing in green. So for C, it's going to be the x-intercept. Oh, that's where y is equal to 0. Okay, so f of x equals 0 if 0 equals the log with base 10 of x plus 5. Okay. And kind of go back to the definition of a log to write this as an exponential relationship. Right, the base of the log is the base of the exponent. The log, the number that's equal to the log, is the exponent, and that's equal to the argument. I think we'll have a better way to think about this after we talk about logs a little bit more and we start solving more log equations. But for now, we're just going back to the definition of a logarithm, and we can use that definition to solve a lot of equations. Okay, so then I'm going to say 10 to the 0, that's 1 equals x plus 5. And I'm going to subtract 5 from both sides, and I'll get x equals -4. Okay, that's C. D is going to be, hey, just find some function values. Okay, f of 5 is the common log, the log with base 10 of 5. No, 5 plus 5. Yeah, it's log base 10 of 5, x plus 5. Okay, so this is log base 10 of 10. That's going to be 1, right? I could write 10 as 10 to the first and use the fundamental identity, or I could say 10 to what power equals 10. That would be the first power, however you want to think about it. Okay, f of 5.01 Let me think about this. This isn't working. Yeah, this is not written right. This is not written the way I intended. 5.01, I think we need it to be -4.99. Yeah, I think that's what I'd intended. Yeah, I'm not really sure what I was going for there, but this will work and get us a useful log question. So that's log with base 10 of -4.99 plus 5. And that would be log with base 10 of 0.01. I think to myself, what exponent do I put on 10 to get 0.01? That's like 1 cent. That's 1/100th of a dollar. So 1 over 100 is the -2 power of 10. Okay, the last one of these would be f of 95, and I'm glad this one's going to work. So it's the log with base 10 of 95 plus 5 is the log base 10 of 100. What exponent do I put on 10 to get 100? That would be +2. Now they want us to sketch the graph of y equals f of x. So what's going on here, I think I'm going to stick with the x-intercept and y-intercept. But, you could use these other function values, f of 95, f of -4.99 to, give you something to look at. All right. So the x-intercept was -4. I'm just going to put that there. And then the domain is x is greater than -5. So I'm going to actually put a kind of a dotted line here, kind of like a wall, like, hey, we're not going to go beyond that. That's called the vertical asymptote, which is not really something we're talking about a whole lot in this unit, but we will be soon enough. I kind of boxed myself in here as far as the y-intercept, because we found that the log base 10 of 5 was like between 0 and 1. So I think I might redraw this. Alright, that's more like it, way out of proportion, so that I can draw this. It look pretty decent. Alright, yeah, that's to my liking. So I've got a positive y-intercept. It's going to happen at log base 10 of 5, which we said was approximately 0.699. Okay, and that's going to be our sketch. Let's move on. Last one is g is going to be the function defined by g of x is log with base 4 of x minus 1. Alright, so domain and range, easy enough. Alright, domain, I'm going to grab the argument and I'm going to set it greater than 0. Okay, so that'll give me x is greater than 1. And for the range, I'm going to have all real numbers because it's a log function. Right, for b, find the values of these things. Alright, well, do that. G of 9/8 is going to equal the log with base 4 of 9/8 minus 1 would be 9/8 minus 8/8 would be 1/8. Ooh, yeah, that's a good one. Alright, so I'm going to go off to the side and say, alright, 4 to the y, because that's really what we're finding is a y value here, g of 9/8. Okay, so 4 to the y is equal to 1 over 8. Okay, we solved equations like this in the last lesson. We just need to rewrite both of these things as a power of 2. Okay, so that means that 2y equals -3, and y is equal to -3/2, which we could call -1.5. And it's, I mean, hardly have enough room to fit over here. Okay, let's shrink them down and move this over. Yeah, that'd be better. All right, so this is equal to -1.5. All right, the next one is going to be g of 3/2. Be the log with base 4 of 3/2 minus 1 would be 1/2. Okay, so we're asking ourselves 4 to what power equals 1/2? Okay, so 4 is 2 to the 2. 1/2 is 2 to the -1. Or you could say it's 1 over the square root of 4 and I'm going to get -1/2. However you want to look at it, I'm going to say 2y equals -1 because I'm big on solving equations, and that's -1/2. Okay, but I might call that -0.5. Alright, and g of 2. And I think, what exponent do I put on 4 to get 2? I think we can do that one without writing it out. That's going to be 1/2 because the square root of 4 is equal to 2. Okay, and 1/2 is the exponent you put on something to take the square root of it. And then the last one's going to be g of 9. Going to be log base 4 of 9 minus 1 would be 8. Okay, so I'm asking myself 4 to what power is equal to 8? This is one where I'm going to need to solve this by writing this. I mean, unless you just see it as taking the square root and taking that to the third power, and it's going to be the 3/2. Okay, it's fine. If you can see how it's going to play out, you don't need to work this all out. But if you're not immediately seeing it, this is the way to go, right? Just keep sticking to what you do know. And I think that, I always say that, yeah, y'all know more than you think. And if you kind of just stick with what you know, you can figure a lot of stuff out. So 8, that is 2 to the 3rd. We're going to set the exponents equal to each other. And then I'm going to say y is 3/2, which I'm probably going to write over here as 1.5. Right. That was the last one of those. C, explain why there's no y-intercept. Okay, well, I don't know, maybe you're like me and just like the first time I read this question, I was like, I didn't just immediately think of something. So if you don't think of anything, do the exact same thing as always. Y-intercept, x equals 0. Okay, f g of 0 is equal to the log with base 4 of -1. Okay, that's bad news. Okay, I've told you that. We can't take the log of a negative number because we're looking for 4 to what power equals -1. It's like 4 to the 0 equals +1. But a positive number to any power is always positive, never negative, never 0. No y-intercept because g of 0 is undefined, does not exist. Okay, that would be why there's no y-intercept. And then sketch the graph of y equals g of x. Not sure why I didn't think about this in the other situations where I had to graph, but I have the ability to switch this lined paper to graph paper. Yeah, there we go. That's great. I don't know why I didn't do that earlier. I don't really prefer to work on graph paper usually, but if I'm making a graph and I've got all these function values, it might be good to make one on grid paper. We hardly ever do that in my class because I don't think it's all that important. We've got technology, we've got the ability to make a quick sketch, but it's good to be able to do this too. All right, so for x's, I'm really only needing x greater than 1, and I'm going all the way out to x equals 9. So I'm going to put that y-axis all the way on the left side over here. I don't know how many. Probably don't need much in the way of y. The biggest y I'm seeing is 1.5, and the smallest I'm seeing is -1.5. Let me count the squares. That's 3, 6, 9. Oh, yeah. I can zoom back in for this. All right. Okay, so this was my y-axis. Axis. I have all of my points ready to go. I can do all of these. So I might start with the x-intercept. Okay, x is always bigger than 1, so I'm going to put in x equals 1 as the vertical asymptote. The x-intercept is going to be where I'm taking the log with base 4 of 1. Okay, but I'll show you that. So for the x-intercept, I'm going to set y equals 0. 0 equals log base 4 of x minus 1. Okay, so that means the base of the log is the base of the exponential. 4 to the 0 equals x minus 1. 1 equals x minus 1. X equals 2. And actually might be the best for us at this point in our journey. All right, so I've plotted my x-intercept. I'm going to plot some other points, like g of 9/8. I don't know about that. Maybe g of 3/2. That's more like it. I can plot that one. And so at x equals 3/2, y equals -1/2. So 1.5, -1/2. That would be right here in the center of that square. Yeah, like that. And then log base 4 of g. Wait. G of 2. Oh no, what did I do? Oh boy. See, when I don't do this in front of an audience, I can get caught making errors and leaving them too long. G of 2. Oh, wait. Okay, hold on a second. Yeah, the computation I did over there would be for g of 3 because I didn't subtract 1. Okay, so this would be log base 4. I was kind of surprised I didn't ask for the x-intercept, and I did for the y, but that makes sense. So log of 1 is going to be 0. Okay, so what I found over there, okay, that confirms it. What I do know now, though, is that g of 3 is log base 4 of 3 minus 1 is 2, which is 0.5. Okay, so I can use that point too. Take an error and turn it into a positive. So g of 3 is going to be 1/2. G of 9 is 1.5. 1, 2, 3, 4, 5, 6, 7, 8, 9 is 1.5. Okay, well, we could probably find a place where it equals 1. So 1 is equal to g of x when 4 to the first equals x minus 1. So that's 4 equals x minus 1. Add 1 to both sides. That's going to be 5 equaling x. 1, 2, 3, 4, 5, and 1. All right, so I want to connect the dots. That's way more points than I usually plot on my graphs, but that's good. It's good change. And then this really is going to turn down steeply and hug towards that vertical asymptote. That was a really nice graph. That's the benefit of graphing on graph paper and plotting a bunch of points and connecting the dots smoothly, so you can produce a higher quality sketch. But just gotta point out, we can always go back here and produce a perfect graph of the thing. Now, I guess I wouldn't say perfect, there's limitations to it. It's not really doing a great job of showing us the vertical asymptote. But what it can do is it can be like, okay, hey, what if I wanted to plug in x equals, I don't know, whoops. Calculate a value, didn't press enter, where x is equal to, I don't know, 4.3. Okay, and it can tell me it's 0.861233. Okay, and our graph is probably not going to be able to do that good. Another thing the calculator could do, if you were really interested in, is you could find like the area underneath the graph between, like 2 and 5. And, give it to us accurate to a bunch of decimal places. And we're just not going to be able to do that with a graph that we produce on graph paper. All right, so that's all I've got to say about graphing. Thanks for watching. Hope this helped.